Hello and welcome. If you're revising for your GCSE computer science exam, you are in exactly the right place. Today, we are going to tackle a huge topic: how computers actually store all the data we throw at them. So let's crack the code on how they handle everything from your essays to your favorite songs. I mean, this is the big question, right? Everything you see, everything you hear, everything you type on a screen, it all has to be translated into the simplest possible language. And that language is just a massive stream of ones and zeros. It's called binary. So how on earth does that even work? And this just shows you the challenge perfectly. On the left, that's our world, It's full of color, sound, meaning. But on the right, that's the computer's world. It's just on and off, 1 and 0. This whole explainer is all about bridging that gap.
Okay, so here's our game plan. We'll start with that fundamental binary challenge, then we'll see how we use it to represent numbers, then characters, images, and even sound. And right at the end, we'll pull it all together into the essential takeaways that you absolutely need for your exam.
So first up, we really have to get our heads around the core idea of this whole topic, the binary challenge. Every single piece of data, I don't care how complex it is, it has to be broken down and represented using just two symbols, a 1 and a 0. That's it.
So let's start with the most direct translation: numbers. We think in what's called denary, or base 10, with digits 0 to 9. But computers, they think in binary, which is base 2. Let's take a look at how that conversion actually happens. And here we go. This is a classic exam question, a real favorite. We need to turn our normal number, 13, into an 8-bit, that's 1 byte, binary number. Let's just walk through it together, step by step. Okay, the best part about this is how logical it is. Seriously, first, you just lay out your 8-bit place values. To make 13, you just ask yourself, can I fit a 128 in there? Nope. A 64? No. Keep going. An 8? Yes. So pop a 1 there, and we've got 5 left over. Now we need to make 5. A 4 fits, right? So we put a 1 there, and we've got 1 left over. Finally, put a 1 in the ones column. Fill in all the other gaps with zeros, and boom, there you have it. 00001101. That's 13 in binary. But wait, it's not just binary. You also need to know about hexadecimal, or base 16. Why? Well, because long strings of ones and zeros are a real pain for us humans to read, so we use hex as a kind of shorthand. As you can see, 4 binary digits, that's a nibble, fit neatly into just one hexadecimal digit. So A is 10, F is 15, and FF is the biggest number you can make with 8 bits, 255. Now here's a clever trick a computer can do, a binary shift. It's a really quick way to multiply or divide. If you shift all the bits one place to the left, you've just doubled the number. Shift them one place to the right, you've halved it. For a computer's processor, this is way, way faster than doing a proper multiplication calculation, and that's why it's so important. Okay, numbers are one thing, but what about letters? What about text? How does a computer store the letter A or even an emoji? Well, the simple answer is, it doesn't. It stores a number that represents that character. And this is where something called a character set comes in. Just think of it like a dictionary that maps every character to a unique number. ASCII is the old school one, great for English but not much else. Unicode is the modern standard. Now it uses more bits for each character, which means bigger file sizes, but it can represent pretty much every single character and symbol from every language in the world. It's a classic trade-off. This quote, and it's from your actual exam specification, highlights something really important. These character sets are totally logical. The code for B is just the code for A plus 1. The code for C is the code for B plus 1, and so on. This makes things like sorting text alphabetically so much easier for the computer. All right, we've done numbers and text. Let's get visual and talk about images. How do you possibly turn a photograph into a long stream of ones and zeros? Well, the answer is the pixel. Every digital image you've ever seen is just a massive grid of tiny colored dots, or pixels. That's all it is. The computer doesn't store the image as a whole. It stores a binary code for the specific color of every single pixel in that grid. So, how much information do we store for each pixel's color? That's what we call color depth. For example, a really simple 1-bit color depth can only show 2 colors, like black and white. But a 24-bit color depth, that uses a lot more data for each pixel, which lets it represent over 16 million different colors. And here it is again, that trade-off. More bits per pixel, a higher color depth, gives you a much more realistic, vibrant image with millions of colors. But And it's a big but. It dramatically increases the file size because you're storing more data for every single pixel. Now, the other key factor for images is resolution. This is just how many pixels are packed into the grid. So an image that's 1920 pixels wide by 1080 pixels high has a way higher resolution, way more pixels, than one that's, say, 800 by 600. And you've probably guessed it by now. It's the exact same trade-off. A higher resolution means more pixels, which creates a much sharper, more detailed image. But more pixels means more data to store, which again leads to a much bigger file size. See the pattern?
Okay, last one. Sound. In the real world, sound is an analog wave. It's smooth, it's continuous. So how in the world do we capture that smooth wave using clunky, separate ones and zeros?
We do it using a process called sampling. Just imagine measuring the height of that sound wave thousands of times every single second. Each one of those measurements, or samples, gets converted into a binary number. When you play the sound back, the computer just reads those numbers in order and rebuilds the wave. It's like a dot-to-dot drawing, but for sound.
And two things determine the quality here. The sample rate is how often you measure the wave. A music CD, for example, takes over 44,000 samples every second. The bit depth is how precisely you measure it, how many bits you use for each sample. More bits gives you a better range between quiet and loud sounds. And, just like with images, a higher sample rate and a higher bit depth both mean better quality, but, you guessed it, a larger file size.
Okay, deep breath. We have covered a lot of ground. So let's boil it all down to exactly what you need to know, what you need to be able to do for your exam. Pay attention, because this is the crucial slide. Okay, let's wrap this up. For that exam, you've got to be fluent in converting between denary, binary, and hex. You need to be able to do binary shifts and know why they're used. You also should be ready to add binary numbers and explain what an overflow error is. That's what happens when the answer is too big to fit in the available bits. You have to be able to compare ASCII and Unicode. And finally, and this is so important, for both images and sound, you have to nail that core trade-off, explaining how factors like resolution or sample rate affect both the quality and the file size. Master these points, and you're going to be in great shape. So we've seen that all this high-quality data, the best images, the best sounds, means absolutely huge files. And that leads us to the next big question, and the topic for our next explainer. Once all this data is stored in binary, how do we make those files smaller without losing everything? In other words, how does compression work? Thanks for joining me.